Hi, I'm Esteban Kuber, a member of the Rust compiler team and of the Rust platform team at AWS. You may also have seen me regularly asking people on Twitter to file tickets for diagnostic bugs. I'm here today to try to convince you that you can contribute to the compiler regardless of your background and provide an introduction about how to go about it. A lot of people have this perception of compilers, that they are black boxes that run on magic and pixie dust, and that to get involved, you need to be unusually technically competent in multiple fields at the same time. There is this idea that only elite programmers can play with compilers. I'm here today as living proof that this is absolutely and fundamentally incorrect. You don't need to know or understand every aspect of a compiler to meaningfully contribute. You don't need to know how optimization passes work to modify the parser. You don't need to know how the parser works to understand how type inference operates. And you don't need to understand how type inference operates to learn how lifetime analysis works. And even though I just used a bunch of jargon just now that may be confusing, opaque, or even intimidating, the concepts behind them are straightforward, and you have resources available to learn about them. And we will explore some of them in a minute. You also don't need to be well versed in the art of language design. You just need to want to do it. And if you have, or think you may have, that drive, this talk is an open invitation for you to get involved, and my hope is that you will feel empowered to look under the hood of the tools you use every day. The Rust compiler is a big program, but it's just a program. And in some ways, it is simpler than many things you may have already worked with. It's not a long-running distributed service. It's not a UI application. Essentially, it takes text files, ingests them into a pipeline, and delivers either a running binary or a bunch of error messages that I hope have been helpful, but that's it. Of course, there is nuance and very advanced aspects of the compiler, but the vast majority of it is straightforward and well modularized. My suggestion for you to get started is first to find problems you're interested in that need solving, then to set up your environment, and last to learn how to navigate the codebase and identify what needs to be changed and how to go about doing that. Finding something to do can be easy. You may already know something you want changed because you encounter a bug, like an internal compiler error or bad behavior, or there is a feature you want in the language. For new features, there is an RFC and major change proposal process that requires sign-off by the relevant teams, usually the language team for anything that affects the semantics of how Rust works, or the compiler team when it's a change to some implementation detail, specifically if it's user visible. This helps us organize ourselves and avoid people spending too much time implementing a feature in a certain way when the teams may already have plans in that area. Otherwise, you can check the backlog and look for bugs that have been identified or feature requests and pick the one you want to tackle. You don't need to go through the entire 5,000 plus tickets to find something that will pique your interest. You can refine your search using labels to narrow the results to a pool that best aligns with your interests and/or area of expertise. There are 3 labels in particular that I find useful for newcomer contributors. The first one is eMentor, which groups all tickets that have an expert in the subject matter, who is available to help and guide you through the process, or who has already written mentoring instructions that you can follow as you navigate the compiler codebase. The second label I find helpful is EEasy. It identifies tickets that require minor changes to the compiler. This is a good way to get acquainted to compiler internals because the level of engagement needed is localized and more manageable. Lastly, I encourage you to consider looking at the PLOW label that identifies tickets that don't need an urgent resolution. They are more of would be nice to have changes. Often, those changes are easy and quick fixes that just never seem to get addressed. Paradoxically, that lower level of urgency means that the pressure people feel when taking them on is much more relaxed. You can take your time to get yourself up to speed without the fear that, let's say, a stable release is going to go out with a regression if you don't act quickly. If you're feeling more ambitious, you can look at recently accepted RFCs and their corresponding tracking items, where you may be able to help bring new features to nightly or stabilize existing nightly features. It's common for these kind of features to have a lot of low-hanging fruit, a lot of polish work that isn't necessary to put together a proof of concept, but that is crucial to match the level of quality people should expect from us. These are not the only labels we use for categorization. We have prioritization labels, labels to mark what team should be concerned with a given ticket, and labels marking what part of the compiler or feature the ticket is concerned with. We take pride in having a relatively well-groomed backlog, so finding the right thing should be easy. And this is an area where people can help, beyond just writing code. Writing documentation and maintaining the backlog are good, well-appreciated contributions. Once you have identified what you want to work on, we need to set up your environment. Ideally, we would all have access to really powerful hardware, excellent Wi-Fi, and an unlimited amount of cookies. As you may know, building rustc requires a lot of RAM. You really want to avoid swapping. You need several dozen gigabytes of disk available and the fastest CPU you can get your hands on. The reality is that not all of us have access to that. Thankfully, the project is currently in the process of procuring cloud desktops for compiler development, to which contributors at large should have access. Stay tuned for further announcements in this area. Now, the feedback loop of writing a change, compiling, and running some tests to verify your changes had the intended effect can easily take longer than 15 minutes on accessible hardware. It's unquestionable that compiling is a time-consuming exercise that can be tiresome. Some strategies to tackle this include making a pot of tea, spending time on Twitter, taking bathroom breaks, or multitasking. Because of this, there is one gatekeeping attribute to thrive when contributing to the compiler. You need patience. Depending on your operative system, your setup will be more or less involved. The first thing you need is getting Git working, cloning the compiler repo in your environment of choice, and have CMake and Python installed. X.py is the main access point to working in the compiler. It lets you orchestrate the build of processes, run different types of tests, and auto-format the codebase. It's pretty much equivalent to Cargo, but exclusively for the compiler. The first time you do this is probably a good time to put the kettle on. The next thing to do is to set yourself up for testing with ad hoc files. I would encourage you to use rustapp to link the compiler you just made as a new toolchain accessible elsewhere in your system. That way, you can write rustc plus dev anywhere in your machine, and it will use your compiler. The same will work for Cargo, which makes it very handy when testing problems that only appear in larger crates or when testing problems for which you haven't found a minimal reproduction case yet. You will also want to get Rust Analyzer working on your editor of choice. A lot of us have slowly gravitated towards VS Code, which will likely be the easiest environment to set up. In order to use a debugger on your compiler, you will need to enable debug symbols, and depending on your operative system, you may have to enable a few other things too. There is a single config.toml file that lets you configure all of this. Fair warning, we are still having some issues with debugger support when working on the compiler due to a combination of some macro trickery we do and gaps in our debug info. In some cases, advancing step by step, you end up going through low-level binary code. Inspecting values can be hit or miss, particularly for enums, complex entities, or variables that have been completely optimized out. Because of that, a common approach is to rely more heavily on debug output, where you pepper your code with debug and info macro calls, and then invoke the compiler with a rustc log flag set to the module and verbosity level you care about. Let's say you've done all of these things, you should be ready to code. Now, let's figure out how to actually go about finding where to make the changes. To help you figure out which part of the compiler you need to work on, I'd like to point to 3 main resources that I highly encourage you to tap. The rustc dev guide, which provides much detail on a lot of the compiler internals and expands on what the workflow can look like. The guide has a lot of useful information, which I try to avoid repeating here, but it is really important to be aware of it. Seriously, if you want to start playing on the compiler's codebase, the best thing you can do is to keep a tab with the guide open. Secondly, you have the Rustlang Tulip chat. It's where you can reach out for help to more experienced contributors. And trust me when I say that we are more than happy to guide you through your exploration of the compiler internals. You can use git blame to identify people who have already worked in the modules you're looking at. And you can also use the expert map, which is a hand-curated list of experts for the different high-level modules. And finally, you can also look at merged pull requests and closed tickets. They are a good source of context when working on something similar to existing features. Once you have everything set up and start trying things out, it is important to get acquainted with some of the concepts encoded in the language and how Rust code ends up being represented for evaluation. One thread I like to pull on to untangle the sweater that is the compiler is to look at error messages. It gives you something to grep for, or you can use the flag treat error as bug, which is nightly only, to get the exact place where it is being emitted, and slowly work your way backwards from there. A compiler first takes a text file, tokenizes it, which means that it splits the text into small pieces that have some meaning. This is when an identifier is separated from parentheses, or when a string or comments are identified. The parser takes those, one at a time, and based on what it has seen so far, decides what the next element should be. This way, the parser starts building an abstract syntax tree. ASTs are a way of representing code in a way that is easy to evaluate. Once we have an AST, we transform it into another very similar looking tree in a high-level intermediate representation, or here. This tree has extra information in it that makes it easier to evaluate correctness and reference other parts of the code. You may already know about expressions. It's the smallest useful unit you will find inside functions. If you have 1 plus 1, that's 3 expressions, a binary operation expression which owns 2 literal expressions for the numbers. Everything you write inside of a function ends up in a tree of these. But we also have a bunch of other constructs. We have items, which are all of the things that can live inside of a file, like types, functions, and constants, amongst others. These two are the fundamental building blocks of all the code we write, and if you're changing code in rustc, you'll be interacting with them extensively. Luckily, they hold a very straightforward relationship with the code they represent, so if you already know Rust, you will easily figure out what is that. Once the here tree is populated, the compiler can start doing its other passes. It can do name resolution, where it figures out what each identifier in the code actually corresponds to. It's when we figure out imports and that vec is a type and vec is a macro. It does type checking, which is making sure that you really don't use a signed 32-bit integer when accessing an index in a vector. It does trait resolution, which means figuring out what traits a given type implements and what trait a method call corresponds to. This also has to account for trait bounds, which has its own very complex level of evaluation. For trait bounds and associated types, rustc models both as obligations, which need to be satisfied. The compiler also needs to do lifetime analysis, where it uses the lifetime that appear in its item signatures to verify ahead of time that all of the borrows in the item can be invalidated. The lifetimes only exist to confirm that everything inside of the item, usually a function, is correct, and that it can be called with the bindings you are calling it with. We have a generic borrow checker error that tells you what all of the lifetimes involved are and try to point at everything that may have caused an issue. But we also have a prior check, where we look at the current environment and pattern match against a bunch of known cases. If any of those cases match, then we can provide a more targeted error. And those are the ones that you normally see. If you can come up with cases where the general error is being displayed, adding a case to handle your special case wouldn't be that hard to do. We just need to figure out how to detect it. After all of these are other things that compiler does, like LLVM intermediate representation code generation, invoking linkers, storing intermediate metadata from the previous steps for incremental compilation. All of those steps are aided by an on-demand query system, a bunch of macros that allow us to avoid recalculating things we've done already by caching them on demand. All of these parts are fractally complex. You can deep dive into a specific part of a single compiler pass and have enough things to do to last a lifetime. But doing useful and fun things don't require digging that deep. When I started contributing was because there was one error that annoyed me, and here I am 6 years later still contributing to the compiler. Once you pull the curtain and realize you can change things, well, it's hard to stop. Now, 15 minutes aren't enough to show the whole development process, and working on big Rust code bases like the compiler is time-consuming. But it is also a very rewarding experience. It is a great way of learning how a tool we all use works. It lets you improve it whenever you want. And it lets you pull back some of the artifacts of language design to have a more accurate understanding of how the language actually works. So, if what you saw made you think, this isn't that hard, and have the time to jump in, please do. Remember, you're not alone. We are all looking forward to helping you make your mark on the project. Thank you for your time. Enjoy the rest of RustConf.